For today's talk, we're very fortunate to have Valenti Bosch-Ramon giving today's talk. Valenti, as you know, is currently a member of the faculty at the University of Barcelona, where he is leading theoretical side of the high energy astrophysics group. Valenti did his PhD on gamma rays from microquasars with Josep Maria Paredes. During his PhD and postdoc years, he also worked closely with Felix Aharonian and Gustavo Romero. Valenti is an expert on the study of high energy astrophysical processes, focusing on compact objects and relativistic outflows, for example, occurring in microquasars and pulsar binaries and young stellar objects, jets of AGN, and so on. Some of his papers on understanding gamma ray emitting microquasars, Fermi acceleration and astrophysical jets, and particularly on the formation of TV radiation in LS 5039 have received high citations. So I just want to welcome Valenti, and I just remind people of the format of the talk, that we'll start by about a 50-minute presentation, Valenti, if that's what you had in mind. And you can start to share your screen. And what I would say is, let's go through, we'll finish the talk, and then we have some focused questions on the talk. And then we should also have a general discussion on any topic related to the talk, or feel free to suggest something. Is there anything else? Anyone? Felix, did you want to add anything, given that today is the first day of the series this year?
No, just
okay. So let's get started. And thanks, Valenti. And please go ahead.
Thank you very much, Rashmi, for this nice introduction. I hope that the talk will be 50 minutes. If I maybe I have to change the pace of the talk, as it used to happen to me, but well, I hope I will be on time.
Yeah, that's fine. I just take the time you need. Okay. Thank you.
Okay, thank you. So, I have added, you all can see the title of the talk here, as Rashmi said, gamma ray binaries hosting a pulsar prospects at the highest energies. I have added here the high mass. This high mass here is because I will focus on high mass gamma ray binaries, which are perhaps one may consider them the canonical ones, those hosting a massive star. There are also some binaries which emit gamma rays. There are at least several of them which host a low mass star, but I will focus on the high mass, as you will see why in a minute. So this is the outline of the talk. I have added quite a lot of stuff here, and I will try to be on time, as I said, but there is quite a lot of literature since the last 10 years on this topic, and it was not easy to pick the most relevant bits. So most of the things I will present here, they are based on my personal view, of course. And also I want to emphasize that I'm probably missing, you will see long citation lists, compact citation lists. I'm probably missing important papers. I want to apologize in advance because of that. There is a lot of material nowadays on these kind of systems from the point of view of modeling, the point of view of observations. So well, I did my best to try to present a coherent picture of the thing, but it's not an exhaustive one. So, okay, I will start with an introduction, then I will briefly discuss the present situation. Then I will very briefly show you the spectra of these high mass gamma ray binaries at the highest energies observed. And then I will go to discuss a little bit particle acceleration and provide some final remarks as conclusions. So, okay, let's start with this personal view introduction. And here you can see to the right of the screen, you can see these kind of sketches. The sketch at the bottom is, let's say, this is done by hand using XFIG, but it's a typical SED for a high mass gamma ray binary. You can see that there are different components. Of course, you may have electrons and positrons producing the radiation. You may have, in some cases, you may have protons or nuclei. Electrons and positrons tend to be favored based on some considerations, in particular cooling times. Here you have, let's say, a typical SED with the synchrotron component or components and the inverse Compton components. So it would be a leptonic type of model or SED. And at the top, you have very sketchy figure representing the basic scenario here. So you have a star, a massive star. You have this black dot here. It's the compact object. And then the massive star produces a wind. The compact object produces a wind as well, a relativistic wind or a relativistic jet. And the outflows here can interact. You end up with different regions depending on whether you are studying the unshocked pulsar wind or jet, or you're studying the interaction with the star and so on. And well, it's worthy also to briefly mention why what gamma ray binary means. I consider gamma ray binary as a phenomenological, not physical term. It typically would refer to an object which has its SED peaked in the gamma rays if you forget about the star. So here in this SED you have the star. It's of course the most prominent feature of the SED, but beside the star you have most of the emission being most of the energy in radiation released in gamma rays. And these kind of binaries are also considered typically to host a compact object. They are not too massive stars, which could also produce the Hawking detectors in gamma rays, and maybe considered gamma ray binaries in a way. But typically, gamma ray binaries concern objects with a compact object. And then, as I said, the presence of the star is very important. So I will talk mostly about high mass gamma ray binaries. Why? Well, because they are among the most powerful galactic sources. And you can see here some examples, typical luminosities in different gamma ray energy bands. And well, as we will see, the great majority, or you probably know, the great majority of the high mass gamma ray binaries detected, they are very high energy emitters. And as we will see, they are quite efficient. They can reach quite high energies. So, okay, some background, some history. Again, it's a simplified personal view, simplified history based on my personal view, sorry. And well, I think that the most relevant points are these three. First of all, in the 70s and 80s with the first gamma ray instruments, it was quite relatively common. It was a common scenario. It was a common thing to propose a non-accreting pulsar being present in a system which was thought to emit in gamma rays. So non-accreting pulsars producing a powerful relativistic wind were quite common scenario at that time. Of course, accreting SNRs were also available, but people typically resorted often to non-accreting pulsars to explain the potential or the potentially detected, because in some cases the detections were not very clear, but let's say the potentially detected sources which were associated to binaries, people used to adopt this scenario to explain this gamma ray production. In the 90s, even if before accretion was already a potential scenario for fueling the gamma ray emission, in the 90s, microquasars became more popular. I think that the most the most important idea behind proposing microcrystals as gamma ray emitters is because they are like scaled down versions of active galactic nuclei, and they were well-known gamma ray emitting sources. And beyond the 2000s, maybe 2004, 2005, pulsar and microquasar scenarios started to kind of compete as explanations for the gamma ray binary phenomenology, because it was in those times that this class of objects started to, let's say, to become let's say well accepted or defined because of the observations. Y had something to do with that, but it was mostly Cherenkov telescopes which started to detect PSRV 1259 or LS5039 or LS161303, which led people to consider these kind of sources as a class, specific class. And basically the two scenarios are, I will try to briefly describe them here. So on one hand, we have the non-accreting scenario where you have a OB star, you have a young pulsar. The pulsar is able to keep the stellar wind far enough. They collide at some location between the star and the pulsar, and the winds form this shock, bow shock type structure. And where these winds collide, one expects to have high energy processes going on and gamma ray emission. The high mass microquasar scenario would consist, it's not that different in a way. It has the massive star with its wind. You have the compact object which produces relativistic jet, and well, on some scales the jet and the wind start to interact as well, and you get high energy processes leading to gamma ray emission probably happening in the jet, or in the jet as it is impacted by the stellar wind. In both cases, you have these relativistic outflows which interact with the stellar wind at some scale, at some distance from the compact object, and this interaction, or the shock winds or the shock jet themselves, they can also produce high energy emission, but this interaction is somehow helping to make the interaction process much richer and leading to different kind of radiation processes in very different energy bands, from radio to gamma rays. And the presence of the star is also very important because it participates providing with the stellar wind and also with the radiation field of the radiation field, which allows inverse Compton to be very efficient in this kind of systems, as well as gamma ray absorption and related processes. So here you have some let's say more detailed examples of the interaction between the pulsar wind and the stellar wind. At the bottom you have two different views. You have a density map for a cat on the orbital plane. Here you have the bluish color denotes pulsar wind, and the more yellow or green or even red color denotes indicates the presence of the stellar wind. Here you have a perpendicular cut to the orbital plane. You can see this in these two plots. You can see the typical structure. One expects this win-win interaction has, at least from relativistic hydrodynamic simulations. I think that to zero order it would be more or less what it is happening, but of course, as I said, to zero order For the high mass microquasar scenario, you have, in a way, not so different picture. If you study the interaction along the orbit between the pulsar, the stellar wind, sorry, and the jet, and you make cuts at different heights above the orbital plane, and you study the density maps at these different heights on the orbital plane, you obtain a structure which is, of course, it's much more extended in the vertical direction, but it's quite similar to what is seen in the case of a non-accreting high mass gamma ray binary. So here already you see that there are some strong similarities, at least qualitatively. And it's relevant to point out, looking at this kind of pictures, that the outflows tend to become turbulent and mixed and so on. So you end up with a quite complex situation. I will talk a bit more about this later. Okay, so let's go to the present situation. Nowadays, there are like, here we have seven high mass gamma ray binaries, which are known, but the compact object is not clear, whether it's an accreting pulsar, it is an accreting compact object. Typically, people tend to favor the non-accreting pulsar scenario for most or all of these gamma ray binaries, but it's in reality the debate is far from being closed. Perhaps the most, no, it's not the only one, of course, but the most, the strongest, the heaviest argument in favor of non-accreting nature in this, for a compact object in these systems, is the apparent lack of accretion features. But still, as we will see, it's not clear at all yet what is going on in all of at least most of these systems. For those systems, we do know whether the compact object is accreting or non-accreting. We have basically three high mass microquasars, about which I will not talk later concerning acceleration. And then we have two gamma ray binaries in which we know there is a compact object that is a pulsar, a non-accreting pulsar. And there are maybe few other accreting gamma ray binaries, but they would be in the category of low mass systems. So, okay, the debate. I want to talk a little bit about the debate, because most of the sources in this class, as I say, they have an unknown compact object, and I think it's important to discuss a little bit why the situation is still unclear. As I said, there are like two basic scenarios for gamma ray emission in binaries. We have the accreting and the non-accreting scenarios, and the arguments in favor of either of them are basically from observations and phenomenology. You could use also some, say, modeling mediated arguments, but I will show later that it's also tricky. It's also noteworthy that there are some scenarios which consist of accreting pulsars. They may be accreting in some phases of the orbit of the gamma ray binary. They may not be accreting, and even magnetars, like very young, extremely high magnetic field, extremely magnetized neutron stars. They have been proposed as possible compact objects. So it's not just, in reality, it's not just either an accreting black hole or a non-accreting pulsar. There are more models out there. So At the moment, there is no observational evidence, conclusive evidence for pulsations or accretion. The mass ranges known for the compact objects are not conclusive either, but there are some hints, at least in some of the sources, which may favor a pulsar. There are, of course, also hints that may favor an accreting source. I don't want to enter into the details of these debates, but it's important to note that the situation is quite unclear. But I would say my personal opinion is that the evidence at this level, let's say the level of hints, is in favor of non-accreting pulsar, of a non-accreting pulsar in these systems, or in most of these systems. And it could be actually that different objects realize different scenarios, or in different orbital phases. One may have an accreting compact object or a non-accreting compact object. Okay, regarding the question of modeling the systems, whether from modeling we can infer the nature of the compact object, the nature of the engine behind the gamma ray binary. The problem with radiation modeling, Monte Carlo simulations, magnetohydrodynamic simulations, is that we have a quite similar basic background, or not background, but like the ingredients of the two scenarios are quite similar, and it's hard to make like predictions that can really distinguish the two cases, and there are several reasons of why it is the case. So we have, for instance, that in both cases the non-thermal emission comes from an interacting outflow, which can be more or less collimated with some complex, as we have seen already, and we'll show later again, with a complex structure. So if most of the emission comes from a similar type of outflow, like a shock jet or a shock pulsar wind, one may expect similar behavior, more or less similar behavior for the radiation coming out from this outflow. There are, of course, caveats, like accretion produces, one expects to have some radiation from accretion, and this should be like quite distinctive. And also we have the shock pulsar wind in the case of a non-accreting pulsar, and this wind may have like also clear features that could be potentially detectable in the spectra of these sources. And so here you would have two ingredients which are not present in both types of scenarios. The outflow structure, as I said, once you have these interacting outflows, you have orbital motion, it tends to produce relatively similar light curves and spectra, and even morphology can be relatively similar. So it can be quite tricky. One can make some oversimplifications, go to a very cartoonish model, and then derive predictions. But as these systems are quite complex, the outflows evolve in a quite complex way. It's not clear whether one can make strong statements from that. It can be helpful, but just heuristic. It's an heuristic tool. And well, okay, just gamma ray absorption and pair production and the radiation from these pairs will be similar also in these two different scenarios. Gamma ray reprocessing is expected to occur in high mass gamma ray binaries, but with the meter, as I said a moment ago, with gamma ray reprocessing, you have similar features from the point of view of what you expect in a high mass binary. Okay, so I will just briefly show you the spectra for the known high mass gamma ray binaries. The idea is that you see from this spectra that these systems easily produce radiation at 10 TeV or even beyond that. So here you have, for instance, example of LS161303. The source was detected very high energy by magic, but this comes from Veritas. It's an accumulation of many hours, as far as I remember. And here you can see that there are points around 10 TeV. So the spectrum seems to reach more or less about 10 TeV. LS161303, it's eccentric, relatively compact B plus an unknown compact object. B star, sorry, with a decretion disk, an equatorial disk, and an unknown compact object. And it's an all friend in the field of gamma ray astronomy. It was detected for the first time by COS-B. Was in the 70s. Here we have PSR B1259 -63. This is a clear case of a pulsar in a B white and highly eccentric binary with a B star. Here you have accumulation of quite many hours as well, and well, it's not very clear from this spectra. From different HESS configurations. The source was detected by HESS in 2005. But the source presents radiation up to maybe, I don't remember very well, but 45 TeV or something like this. 40 TeV, it reaches very high energies. So it's remarkable. Here you have LS59. This is a very compact, moderately eccentric binary with a no main sequence star and an unknown compact object. This source was detected by HESS at very high energy, but it was already in the YGRET era, let's say. It was proposed by Paredes and collaborators that it was a gamma ray source because it was very nicely inside the error box of one of YGRET sources. And here from this spectra from HESS, you can see that there are points beyond 10 TeV. Maybe it reaches 20, 30 TeV, something like this. In the case of HESS J0632, this is an eccentric, relatively white binary with a B star and a compact object. Again, here, the source was detected, I think, by HESS in 2007, but then it was not clear. It was not known whether it was a binary. Like several papers came out later on until it was clear it was a binary system with a high mass star. But anyway, the point is to show that, again, you have points in the spectra. Here you have a spectra for different orbital phases up to around 10 TeV or something like this. I'm speaking very approximate in a very approximate way. I mean, I don't want to enter into the details of the analysis, whether these points are very significant. I just want to show that the spectra tend to reach easily these energies in most of these sources. Here we have one FGL J1018. I think it was detected first by Fermi, and then has detected the source. But anyway, the question here is that you have points up to maybe these black points reach about 10, 20 TeV. This is overlaid with LS59 data just to show similarities. This system is very similar. It's quite similar, maybe not very, but quite similar to LS5039. It's also compact, a bit less compact, moderately eccentric perhaps. I think eccentricity is not clear. And it hosts no main sequence star and an unknown compact object. Here we have PSR J2032. This binary pulsar was gamma ray binary The binarity was proposed by I think Line et al. 2015, but the very high energy emission from this region, it's also an old friend for the very high energy community, as HIGRA detected the source. I think maybe the first paper was Haronian et al. 2002. I'm not really sure, but it's not clear whether the HIGRA and later MAGIC Veritas source, this extended source, corresponds to PSR J2052, but it seems plausible that there is a strong connection. Andrei Bikov was discussing this in one of the talks of CDY-Initiative. And here you can see, okay, maybe it's not as clear as in the previous cases, but the source reaches few TeV energies, more or less. And here we have LMCP3. This is located along a large Magellanic Cloud. It's an extremely powerful source, model eccentric, compact. It's like an overgrown LS-59, something like this. It hosts, I think, an old giant, maybe, an unknown compact object, and we have here points more or less around 10 TeV again. For FGL J1405, it's not known whether it's a very high energy source, but it's a powerful GeV source, and I wanted to add this one here because it's again relatively similar to LS-39 and one FGL 1018. And finally, there is HES J1832, which I think it was proposed by, I'm not sure whether it was proposed for the first time, but Eggers et al. 2016 proposed that this source was a binary. And well, I think that maybe the strongest hint that this source is a binary comes, or evidence comes from X-rays and to a lesser extent from Fermi, which show some level of periodicity. In the case of Fermi, it's not, I think it's not significant, but it's suggestive. So it's very likely a binary system with an O-type star, perhaps, a non-compact object, moderately wide. And the spectrum here, it's also close to, reaches close to 10 TeV. So with the exception of 1405, all these high mass gamma ray binaries are quite efficient accelerators, as you have seen. And I hope I have been able to provide you some idea of the basic physics behind what is going on in these systems. We have all these outflows interacting and propagating. There are plenty of, as we will see now, there are plenty of places where particles can be accelerated. There are different mechanisms. I will focus now on the scenario with a non-accreting pulsar. Most of the things I said before were quite general. Now I will focus on the non-accreting pulsar scenario in order to illustrate the different places where you can have acceleration. You may have some type of shock acceleration, kind of Fermi one, although the shocks can be, at least some of the shocks can be strong relativistic, so this could be a problem, but diffusive shock acceleration process mechanism could take place. Fermi 2, because a lot of turbulence can develop in this interacting outflows. Fermi 2 could also be relevant. Shear acceleration, because you can have shear flows. If the pulsar wind is magnetized enough, one can have some pockets, some regions where different polarity field lines could reconnect, potentially accelerating particles. And there is also some possibility to have the converter mechanism, which is a special, let's say, a specific mode of particle acceleration in relativistic shocks. This mechanism could happen in the environment of the gamma ray binary. Okay, and now I want to show in some more detail the different regions where you can have particle acceleration. So on one hand, we have the unshocked pulsar wind. Here you have to the left and bottom of the slide, you have a zoom on a relativistic hydrodynamic simulation, where you can see in more detail the density map on the equatorial plane of the binary. And this region, I hope you can see my cursor, my mouse. This region would be the unshocked wind. The unshocked wind is shocked by the stellar wind. And since there is orbital motion, of course, the interacting structure tends to go to get deflected in the opposite direction of the orbital motion of the compact object. And the unshocked wind itself can be interesting from the point of view of high energy or very high energy emission. Then also we have the shock itself against the stellar wind, and then we have this effect of the orbit, which translates leads to the generation of a strong shock, which is punching, let's say, from the side against the orbital motion direction. This shock structure, this shock outflow. And this, we typically call it Coriolis shock, this related to a Coriolis force. This shock tends to force the closing behind the pulsar. So we have a strong shock behind the pulsar as well. And as you can see here, you have different regions where you can accelerate, particles. Shocks may be more, let's say, more or less oblique, depending on the region where you are. And then you have, from these interactions, I mean, one sees the development of Rayleigh-Taylor, and would be more appropriate to say Riemann-Meshkov instabilities, because there is some kind of impulsive Rayleigh-Taylor instabilities going on in the boundary between the two shock winds. On the leading edge of the interaction structure. Also, Kelvin-Helmholtz instabilities could take place because we have here very different velocities for the shock pulsar wind and then shock and the shock stellar wind. Actually, the shock pulsar wind are shown very clearly in 2008 by simulations by the simulations of Bogovalov and collaborators. The shock pulsar wind gets accelerated in this region. I'm not sure you can see the cursor in the region behind the pulsar, and even the shock pulsar wind becomes highly relativistic again, but it eventually gets stopped by the Coriolis shock, and then these instabilities lead to turbulent development, weaker shocks. If we go to the top of the slide, to the right, you can see a wider perspective of the interaction region. These simulations are they were 3D simulations with low resolution because it was very heavy. It was a very heavy simulation, so resolution could not be very high, but still we can see quite a lot of kind of turbulent development. So the instability growth, and there is mixing of pulsar wind and stellar wind. Of course, there are numerical artifacts here. One can discuss about the details, but probably physically at the qualitative level, it's quite clear that the structure is quite unstable and gets easily disrupted due to the effect of these Coriolis shocks and the Coriolis force, which is forcing the structure to bend very strongly due to orbital motion. So in this region, you could have also this turbulent acceleration or perhaps shear acceleration. And if you go to larger scales, this is a 2D simulation, but qualitatively, we believe it's quite reliable at the qualitative, as I said, at the qualitative level. we can see that the spiral which forms due to this, due to orbital motion, gets completely disrupted after one turn or two. So it's a very messy environment, and one expects that the pulsar wind and the stellar wind will tend to form a more or less unified, partially homogenized outflow, which is heavy mass loaded, of course, by the stellar wind, and therefore cannot be reaccelerated again up to relativistic speeds. But it can still get some reacceleration because the pressure far away is much lower than the pressure on the binary scale. So you can have reacceleration up to mild relativistic velocities, for instance. But you get something which is, as you can see here, kind of clumpy and strongly mixed. Of course, the role of the magnetic field can be very important because it can either enhance or inhibit the development of these instabilities and the mixing and so on. So, although it will be very costly, it's very important at some point to thoroughly study these interactions using also the magnetic field or different configurations of the magnetic field in the pulsar wind. Sorry, I think that one of the few simulations in the context of binaries with magnetic field was done by Bosch et al. 2019, but it was done just for the inner region of the interaction region. So to study how it develops farther away, it requires much more work. But I think that even if the magnetic field can change the picture significantly, qualitatively, I would expect not very different outcome, but it's again, my personal opinion. I want to go a bit further. Yes, I want to mention something else. No, I think I already covered the whole slide. I want to go farther from the binary. So if you go farther from the binary, you still have things going on. And to the right, you have an example of what happens when you have a highly eccentric system. So PSR B1259 is a highly eccentric system. PSR 2032 it's also highly eccentric. HES J0632 it's maybe highly eccentric. It's not clear. And LS16103 could be also quite eccentric. It's not clear. And in these kind of systems, one expects to have far from the pulsar, something like this going on. So here you have this spiral formation. This bluish material is the pulsar wind mixed with, to some extent, but not too much with the stellar wind. The yellowish greenish material is more stellar wind. Here you can see from afar the interaction structure at a particular orbital phase. Since it's a quite eccentric system, this interaction structure changes its typical scale with orbital phase. So in the plot at the top, you cannot see the system basically. Sorry, the system. You cannot see the region where the Coriolis shock starts to bend the structure. Here it's invisible at the top. At the bottom, you can see this region, more or less. It's much larger, so it's visible here. And you can also see how there is a strong asymmetry in this interaction structure, because this is, of course, an orbital plane cut. We are showing here a density map. And you can see how the spiral gets completely destroyed in the direction of to the left, and this direction is the pastron direction of the system, because as the pulsar wind spends most of the time pointing in that direction, the spiral structure gets pushed very strongly by the pulsar wind, and in addition of disruption and instability and so on, you have this strong push in the pastron direction. These scales are huge, like you have the order of 1,000 of the binary separation here. The previous plots I was showing, they were like tens separation distances Here you have 1,000 separation distances. And you can see how in these highly eccentric systems, the interaction structure becomes like kind of one side broad, calling broad jet kind of, due to the high eccentricity. In general, this mixed flow made of pulsar wind and stellar wind tend to could form easily kind of nebula. Something in between a massive stellar bubble made of the stellar wind, made by the stellar wind, pushing on the ISM, for instance, and pulsar wind nebula. So this kind of a structure, which would form at very large scales, let's say fraction of parsec, would be in between these two cases, because here you have a massive star providing mass and to some extent momentum. You have a lot of energy coming from the pulsar wind, but very little amount of mass and not so much momentum. And you will get some kind of mildly relativistic, or not relativistic but fast reaccelerated flow mixed of wind and pulsar. A mixture of pulsar and stellar wind, which will interact on large scales. You may get cometary tail if you have a fast-moving binary, of course, as well. And it's nice to see this example where you have, in the case of PSRJ 2032, since this system is very, very eccentric and most of the time the pulsar is far away from the star, there are these hints in X-rays. Maybe they're not very clear in this image, but there are hints in X-ray of a kind of torus plus jet-like structure. Okay, this has been recently presented, and I think it's being studied. I'm not sure how significant this is, but it's interesting, and one would expect such a structure if one understands that the system is very, very eccentric and the role of the star is only important for a small part of the orbit. There are several works presenting X-ray evidence of large scale, like arc minutes, large scale X-ray emission from several of these high mass gamma ray binaries. So they are probably related to the flow termination or something not far from that. And here I want to point out that the acceleration can be quite important. So if you apply just the Hillas limit for typical parameters, size of the accelerator, magnetic field, which is relatively weak compared to the energy density available, you can easily get 300 TeV applying the Hillas limit. If you compare acceleration rate and escape or adiabatic cooling, you can get easily close to 100 TeV for a mild relativistic outflow with a quite efficient acceleration process. So like 10 times slower than the electrodynamical limit. If you have diffusion escape, you can still get like about 40 TeV for these typical values of the magnetic field and the size of the accelerator, and diffusion coefficient, which is 10 times the bomb diffusion. And from pure synchrotron losses for electrons and positrons, you would get something about like tens of TeV for a quite efficient accelerator, as I said, about 10 times slower than the electrodynamical limit. So you can see that you can justify easily the presence of particles reaching at least tens of TeV. And you can extrapolate and even think about what happens far away from the system. If you assume that you have mostly perpendicular magnetic field, which is being advected away, you will have some kind of constancy in the product of the typical size, the radius, let's say, and the magnetic field, more or less. And if you keep this R times B constant, roughly constant, you get similar maximum energies far from the binary. If you have, for instance, a shock in the interstellar medium, when these mixed outflows end up colliding with their surroundings. And about the shock wind, I want to point out a very interesting process, which is basically the converter mechanism applied to the environment of the unshocked pulsar wind. Because in several of these systems, we do have quite high luminosities of MEV photons, and this MEV radiation can produce some, even if the opacity is relatively low, this MEV radiation can produce some pairs inside the unshocked pulsar wind. And these pairs are produced more or less isotropically, isotropically inside the pulsar wind in the lab frame. So it means that the pulsar wind basically boosts these pairs, picks up these pairs and boosts by gamma squared these MEV pairs, more or less. And these MEV pairs, once they get this kick to gamma square energies, they cannot cool very efficiently because their energy is too high to cool efficiently through inverse Compton due to the Klein-Shina effect, and the magnetic field in the pulsar wind is significantly reduced by Lorentz transformation of the magnetic field. So until they reach the shock, this component of loaded pairs, gamma square, boosted gamma square by the unshocked pulsar wind, until they reach the shock, they don't lose much energy. And once they reach the shock, they can produce a significant amount of synchrotron radiation in particular, because then magnetic field matters. And this is interesting to point out this because this mechanism may solve several mysteries in several of these gamma ray, high mass gamma ray binaries. And you have here some names. On one hand, you have very efficient acceleration, which can provide you with the required energies of the particles. This component in the pair loaded wind will be very hard because surrounding gamma square, more or less, will be quite hard. It will not have a strong low energy component. Of course, there will be also the particles in the pulsar wind, which were moving from the very beginning. The pulsar wind, on average, is slowed down by the presence of these extra pairs. But you will have probably a gap between the primary population of the pulsar wind and the secondary population of the pulsar wind, which allows you to avoid some tricky problems. For instance, cascading. If you have a very hard 10 TeV or tens of TeV spectrum, you will not get much cascading features. You will tend to have, if the radiation is produced in a very dense radiation field, you will tend to have a rather flat or relatively flat TeV spectrum. And you will not see, for instance, large amounts of radiation in the percreation threshold corresponding to the field of the star, which is around tens of GeV. So it's interesting because it may explain some features of the spectrum in the case of, for instance, LS5039. And then these pairs which reach the shock, these ultra high energy pairs or very high energy pairs that reach the shock, they produce synchrotron around this maybe 10 MeV, something like this. And these sources have been seen at these energies very likely by Comtel. So Werner Kollmar has been working a lot on that, and it seems to be the case. And it means that, well, you could explain this MEV component, this MEV component of the spectrum from these pairs accelerated by the pulsar wind, unshocked pulsar wind. And the unshocked pulsar wind itself becomes smoothed by this pair loading. So the primary component is not so energetic, so it can somehow go unnoticed because these pairs will produce inverse Compton. But if they are not too energetic, they may not be seen in the spectrum. So, well, I think this is a promising mechanism for high mass gamma ray binaries, at least some of them. And just to conclude, some final remarks. Very obvious thing, I think pulsations, mass characterization are most important to decide between a non-accreting scenario versus an accreting scenario. And I want to point out that although these systems may efficiently accelerate particles on the scales of the binary or a bit farther, since this outflow is outflowing mixed with the stellar wind, so there is a strong mass loading, there will be adiabatic losses, and the mass loading prevents from significant reacceleration of the outflow. So these energetic particles may lose energy in the way to the ISM. But once they reach the ISM, they could produce again a population of very high energy particles. So they may indeed be cosmic ray accelerators, maybe up to hundreds of TeV. And then you could have protons and nuclei to pick in your acceleration, to pick up in your acceleration process. And these systems, they may provide from their energetics maybe a 10% of the energetics of the cosmic ray, galactic cosmic rays, sorry, maybe a 10% or something like this. Their energetics can be quite high. Like we know already, like 4 sources within 7 kiloparsecs, and there could be like 10 with similar energetics, so you can get quite high luminosity budget for high mass gamma ray binaries. And that's it. That's all I had to say. Thank you very much.
Thank you, Valenti, for comprehensive reviewing the theoretical, phenomenological aspects of these exciting objects. Questions? Actually, we are already 1 hour, so maybe we could combine questions with discussion. So just let's start discussion directly, asking question to Valenti or commenting. So, Evgeny Derishev, yeah, I see that. Yes, Zhenya.
Valenti, I have a simple question about your introduction. You said that accreting objects are almost excluded as the companions because we don't see the signatures of accretion. And my question is, does it cover also the situation, possible situation that these accreting objects have advection-dominated flows, so they are inefficient in producing this kind of signatures?
Can you see what I'm marking now in the slide? Can you see the slide? Final
yes.
remark?
Yeah. Okay. Okay.
So no, I wanted to, maybe I was not clear enough. So I don't think that this possibility is excluded. I'm just saying that people tend to rely on the absence of these features, but I wouldn't be so, I wouldn't be too confident rejecting the possibility that you have this mode of accretion, and therefore you wouldn't see much accretion features in the spectrum.
But in this sense, you exclude accretion onto neutron stars because you think that it cannot be radiatively inefficient, right? Yes,
so there are some cases in which some mysterious flares have been seen, for instance, for LS-161-303 in X-rays, very bright flares, but they were weird. There might be some source confusion, might be. Still, it's quite compelling, and in this case, maybe we are seeing some activity from the compact object itself, which may be kind of, I don't know, not magnetar, but quite young neutron star. Who knows? But in general, yes, we don't see these features from a surface of a neutron star, for instance, accretion through the poles or accretion directly to the neutron star surface. We don't see these features, so yeah.
Yeah, I see. Okay, thank you.
You're welcome.
Valenti, one question I don't see, and I have one question regarding your comment that just on this page we say large-scale outflow medium interactions might be suitable sites. So What do you mean actually? Could you say a bit more about this statement?
Yeah, it's important, but well, I couldn't devote much time to it. So the point is that here we have this idea that you may so here you have this sketch where the mixed outflow goes away from the binary system and eventually interacts with the environment and forms some kind of nebula. So it would be between a stellar bubble and a pulsar wind nebula. And there the conditions can be quite good for particle acceleration, as we know that this is the case for the shocks of the I don't know, for instance, in the graph, we have the pulsar wind, which gets shocked, and you have non-thermal particle production, or you may have in bubbles of young stars, massive stars, you may have production also of cosmic rays, like hundreds of TeV protons. And the conditions in this kind of systems would be similar, because you have maybe 10 to 9 centimeters per second or even more mixed outflow loaded with protons from the stellar wind, which goes away and eventually is stopped by the ISM with a very strong shock. And with you would have conditions which are very much reminiscent of those, even in supernova remnants, although supernova remnants are not persistent sources, are like, I mean, explosive ones. And that's, I think that it's a good kind of phenomenological argument. That I think it's a good phenomenological argument to look deeper into this possibility, like the interactions with a larger scales could produce cosmic rays, maybe not TeV, but probably hundreds of TeV or 100 TeV. I mean, you have the ingredients there for that.
Yeah, but do you have estimates, or because, I mean, you are saying that because these days is fashionable, this PV, or you have?
No, I'm saying it's here somehow in a very simplified way. Here you have these estimates for the phenomenological estimates for the maximum energies. And if you assume you have, for instance, toroidal magnetic field, which is being dragged away by the outflow, and the outflow grows accordingly, linearly with distance, you will have this combination of RB, the radius times the magnetic field, more or less constant. So you can use this kind of estimates to try to understand what happens at larger scales, because R times B will be more or less constant. So in the termination region of this kind of outflow, you may get these energies, like 100 TeV or something like this. And if you tweak a bit the parameters, you can even get higher energies. And there, the synchrotron, for instance, synchrotron emission is not a problem for electrons and positrons. If we think of protons, certainly it's not a problem either in the binary system. So you can easily get this kind of values also far away from the binary. Because the problem is that if you accelerate 100 TeV particles close to the binary, they have to propagate in a medium which is expanding. They exert work on this medium, and they also exert work on the stellar wind, which is mixed with them. So you eventually lose a lot of energy in this way. You need another shock later on, for instance, to reprocess the energy and get again a re-energized cosmic ray population.
Yeah, but 1 month ago we had a talk by Andrei Bykov, who was talking about interaction of the pulsar wind of the stellar wind. And the statement was that you could get in this interaction, you could get particles, protons, accelerated to be PV energies just inside the binary.
Yeah, but this binary, first of all, I'm not sure whether it's plausible in the case of PSRJ 2032, but it might be because it's a very weird system. So in this case, you have extremely wide binary, and there you will not form this kind of spiral of mixed stellar and pulsar wind. So if you have a highly eccentric system, you will not mix the winds, and if you accelerate particles relatively close to the binary, they may escape easier. I'm not sure it's really the case, but in principle, they may escape easier, and maybe they could reach the Higrasor region, for instance. That would be very interesting, by the way. So yes, I mean, in principle, I could try to find ways to explain that, but in general, it's highly non-trivial to put this, to keep particles energized from the binary system too far away in general.
Yeah, it's interesting just to note that there's a tendency now. You showed this 1259 spectrum, the latest S publication. Yes. I mean, there are some amazing energies there. If you look there, it's going tens of TeV, tens even more than. So it is, and it seems now is a trend just to see more and more high energies from binaries. So this is quite interesting results. So it should be addressed somehow. I don't know. Could be explained this 20, 30 TeV gamma rays, if not more, from 1259 in these standard considerations or not?
Well, using phenomenological arguments, you can. I don't think, but I don't think it's easiest to find the specific mechanism to get that. I'm excited with this idea from Zhenya and you from 2012 about the acceleration by the unshocked pulsar wind, for instance, because it provides you a way to get this gamma square kick and get very, very high energy positrons and electrons in the wind. And this process seems kind of clear in a way. Maybe it may not work, but at least the process is clear. And there are other processes which are very complex, like relativistic shock acceleration, the level of the turbulence in the magnetic field, where you can really accelerate particles up to very, very high energies in these kind of environments. And as you can see from the simulations, one expects very complex environments. So the problem is that we have this picture, qualitative picture, which may be relatively robust already, but it opens many open questions, as what you said, like whether the acceleration mechanism can be, a specific mechanism can be as efficient as to get this. But from phenomenological arguments, tens of TeVs seems possible.
Okay, thanks. So Maxim, you have a question?
I have a question about efficiency of acceleration of particles. If you have, Valenti, could you come back to a slide where you show your estimations for high energy? Yes, here. You have adiabatic losses, like which limits your maximal energy to 90 TeV and diffusion 40 TeV. And if you remember, this work was done before idea what you can have acceleration of wind, and it could be much faster adiabatic losses. Am I right, or it's in relativistic region?
This is so in a region of the shock pulsar wind, you have this reacceleration, which leads to a strong adiabatic cooling of the non-thermal population of particles, which may be there in the shock pulsar wind. This is shown. I mean, this is the canonical paper by Bogolov and collaborators, 2008. But you have many other regions where you could accelerate particles, and you could avoid for a while at least this constraint from adiabatic cooling. But then again, what they said, so if you go farther from the binary where the shock mixed flows start to reaccelerate, then again, you have this adiabatic cooling there. So that's why you may accelerate particles up to very high energies, produce very high energy photons, but these very high energy particles, even protons, they don't survive for long with those energies. And then you need some, maybe potentially you may have this reacceleration farther from the binary, right? Or in the case of this scenario in which we had been working, like you have this pulsar wind directed along the apastron direction, mixed with a stellar wind, and there you have plenty of relativistic shocks going on with the stellar wind pieces, the pieces of the spiral that were disrupted by the pulsar wind. So there you could have also like efficient acceleration in some spots, and you may see that in X-rays, for instance, as it was discovered by Pavlov in 2015 and presented in other works as well. Is it related to your question, Maxime?
Yes, yes.
So it's like you have different regions, and somehow to make a clear statement, singular statement, is complicated.
Paolo, Paolo, you
Yeah.
have a question, right?
Yeah, I just had a question. To what extent is constraints from like absorption of the gamma rays relevant? Because if you really, a lot of spectra seem to go out to 50 TeV or something, and in my experience, it's not so easy to avoid features or reprocessing.
Yeah,
so does that argue that the stuff is coming from very far away in that case? I know Dimitri at one point had a paper with a MEV bump or something from cascades, but I don't think there's strong evidence, right? So you tell me.
Yeah. So the point is that with Mitya and Felix, we were discussing this for a while, for quite a long while. We had a problem with cascading, and the most reasonable, I think that the most reasonable way out was to assume that the TeV emission comes from, let's say, a distance of few times the separation distance. There you still have features in the light curve which are related to the orbital motion. There you still have very efficient radiation, but you don't have a strong absorption. But there is another way out, which I didn't expect was possible. But if you have this, let's say, one-shot acceleration in the pulsar wind, you produce this kind of secondary population, very high energy particles in the pulsar wind. They will not cool significantly in the pulsar wind, so they can propagate for a while until they reach the shock. In the shock, they will produce a lot of synchrotron in the MEV, more or less. But the interesting thing is that they will also produce TeV emission, of course. At some, I mean, maybe not, they will not cool completely through TeV emission, but they will produce still TeV emission. But this TeV emission will be extremely hard. So if it's extremely hard, then you can fill the lower energy part of the spectrum with reprocessed emission without worrying about strong features of cascading. I'm not sure I was clear.
Yeah.
Was it clear, Paolo?
Yep. Is there some fine tuning involved though to make it look so smooth? I mean, to be.
I don't think we know that for the moment. There might be, maybe you need some fine tuning to really explain one particular source. But in principle, it's true that you would expect the secondary component quite naturally without much fine tuning.
Yeah, no, that's true.
If you have this pair creation in the unshot pulsar wind, and the nice thing with these sources is that they are all bright, let's say they are likely bright COMTEL sources, because, well, one cannot get much from COMTEL data.
Yeah.
But they are, apparently they are detected by COMTEL, so they should be bright COMTEL sources.
Thanks.
Thank you.
Valenti, maybe I have one more question. If you are talking about these mysteries of LS5039, I didn't follow the recent developments, but I just, there is some progress in interpretation of GV emission of this source. I mean, because if I remember the argument that is a pulsar, because spectrum looked like a typical pulsar spectrum, and then we found the modulation of this emission. So was not clear how could be modulated pulsar emission. I mean, modulated with the binary period.
Yes, there is something interesting. So on one hand, you have this orbital modulation, which is quite clear, quite strong, maybe a factor of a few. And then also you have a strong modulation, I'm not sure modulation is the word, but the strong variability in the long-term emission from the source in GeV. So if you look at the light curve from Fermi, Mitya, I think first author is Yoneda. They have a recent paper with studying Nussdal data and also Fermi data, and they show at different energies this behavior on the very long term. And at different energies, you can probe different regions of the GeV spectrum. And they show also like a strong variability or significant variability in this GeV emission in the long term, like month scales during years and years. And you have significant changes of the flux. And at different energies. So even if you may have some magnetospheric component in some energy range, which may be dominant in some sub-range of Fermi data, of the Fermi spectrum, it's strange that it's changing along the orbit. Maybe there are hints that some spectral points, spectral points are not changing with orbit. Other spectral points are clearly changing, so you get this modulation. But in the long term, there seems to be a modulation in all energy bands. And I think it goes clearly against this at least as a dominant component, this magnetospheric emission. And there are also new hints of like kind of at about 100 MeV, you have something which may be like, if you look at the spectrum, it may nicely fit with what Comtel sees at higher energies. So this would support Comtel data somehow. And you may have like different components showing up in the GeV from the behavior at different energies. The spectrum is complex in this from 100 MeV to tens of GeV. The spectrum is quite complex. But I don't think we have gotten anything really compelling. Like yes, it means this or it means that. I think that very much in general, situation is similar. Sorry, it's similar to what it was like 10 years ago. But there are, of course, new data. One can think more. One has to devote time to that. I don't know. It's complicated. It's complicated to at the moment to put everything in one, one coherent conceptual structure and derive some clear prediction. But at least things look interesting. There is a lot of material to think about.
So what is the strongest argument that the Compal project is a pulsar in this system?
If one puts aside the possibility of X-ray pulsations, which were discussed by, I forgot, maybe Karvalsev, I forgot the other authors arguing that it was probably an artifact, but there could be pulsations, as Yoneda et al. 2020 showed. But if we put aside this, I think that this, as what I say, the strongest argument is the apparent lack of accretion features in the X-rays, which is kind of phenomenological argument, and it's somehow compelling, but it's not the determinant. Then you have other lower order, less significant arguments, but they would rely on similarity, analogy.
Yeah. So Reshmi has a question.
Well, I just have a quick question. So you mentioned the NuSTAR paper that came out. There were several NuSTAR studies of X-ray of these gamma ray binaries jointly with Hess, I think, and there was one with Veritas. Do you have a particular one in mind that you were referring to? Do you know which one?
I remember there is this NuSTAR, I think NuSTAR and Veritas paper on
Yeah, on,
LS161303, but I was thinking on LS5039.
okay. Mhm.
And it's a paper by Yoneda et al. 2020 as well.
Okay. Mhm.
And they show Nustar data compared with Susaku data, and which is much older, and also Ishishita, maybe 2009. And then they also add Fermi analysis there.
Yeah, and I think that the MEV predictions, I think that will become hopefully relevant. There are some missions that are being planned now for MEV. I mean, COMTEL didn't have the sensitivity, but I think it'll be important to keep an eye on what the MEV predictions are.
Yes, yes. For instance, I'm particularly interested. I know that there are other instruments, but for instance, I've been interested in HERT, which is a project. I think it's a collaboration between people. I mean, between China and countries of the European Union.
Yeah.
And there are other instruments which we want also to prop this region, and it's going to be really interesting.
Yeah.
When one of these projects appear, become realized, because yes, what you said, it will get it will provide a lot of information about these specific binaries, because we know that several of them, they have this large MEV luminosity. So.
Okay, thank you. Thank you also for your excellent talk.
Thank you, Rashmi.
No, this still is Rashmi. So one more comment. I mean, I don't see questions. Let me just to use this opportunity. Well, say about this again, coming back to multi-TV, tensor TV emission, that it's this object, at least the both actually LS and 5039 is in the field of view of Lhasa. And if this and has, at least, I mean, in the original paper, we claimed 20 TV, maybe even higher energy. So, and Lhasa has a much higher, larger sensitivity at these energies. So something very exciting. I mean, it could come from Lhasa in this area as well, because, I mean, if it's really, they are going so high energies, then it's a perfect Lhasa range above 20, 30, 40 TV. It's not so easy, but still it's just, so some more I'm talking about, is prompted about these new observations. What would be key observations of this type of object? I mean, just generally you could say just keep observing them. I mean, but to some extent, since these are the steady state sources, steady sources, like, so all the instruments are saturated more or less. I mean, sensitivity, what they can do much more. Of course, CTA could make one step forward in the sense that it could measure energy spectra, different phases. It's just important not to just energy spectra average large beams, but Lhasa, I think it's just could bring a lot of interesting things. So the near future, probably again, these days we are learning that a lot of things are coming from Lhasa in different areas. And surprisingly, something could come also in unfortunately, as I said, this both LS objects are in field of view of Lhasa. So I think that could be another interesting results, exciting results from Lhasa side.
Yeah, actually, I don't used to talk much about instrumentation because I feel a bit scared of it. But I
no,
think
that is good, because I'm just, because it's now.
No, Felix, let me finish.
More about
what I wanted to say is that indeed I had Lhasa in mind when I was thinking about this highest energy part of the spectrum, because I know that these sources could be detected by Lhasa at some point, and if it is the case, it's going to be extremely interesting. So it was in the background of the talk somehow.
Yeah. No, I just mentioned in the sense, what do you expect from near future? I mean, with CTA, it's clear it will be better because we are lacking some sensitivity rate, detection rate. So CTA would improve that, but what comes for near future and probably is like hard X-ray stuff. And I don't know what specifically New Star can do. Of course, I mean, clear that can do a lot, but more specifically, but for, I mentioned LHAASO, just not just general, we're often talking about LHAASO these days, but just simply for this specific case, that could come really very, very interesting results. And I'm so optimistic because in HES, I think we do not have doubt in detection of 20, 30 TV gamma rays for those LS5039. So that is very good situation.
Yeah.
So if there are no more questions, we could conclude, Reshmi, right?
Yeah, I think so. I think we're at the end of our allotted time. I think thanks again, Valenti. That was an excellent review and comprehensive talk. It's nice to get all the details of the observations, and the discussions were great. So thanks everyone for joining. And just a reminder that in 2 weeks, that is, I think it's January 26th, we have the next CDY talk. So I hope you can join, and see you there.
Thank you very much.
Thank you everyone.
Thank you.
Yeah.
See you.
Okay, the next talk is on the HAWK Gamma Ray Observatory. Thank you.
Thank you.